Spring of 1945, a repair depot outside Munich. 3 Wehrmacht mechanics stand over a disassembled American Sherman tank, its Continental R975 engine laid bare on the workshop floor. Oberfeld Weibel Karl Brecht runs his fingers along the cylinder walls, checking for wear patterns. He expects scoring, carbon buildup, the telltale signs of an engine pushed beyond its limits. Instead, the bore surfaces are smooth, almost mirror-like. The piston rings show minimal wear. The valve seats are clean. Brecht checks the maintenance log captured with the tank. 2,140 kilometers since its last major overhaul. He shakes his head slowly and mutters to his assistant, "Das ist unmöglich." This is impossible. Under Wehrmacht technical doctrine, a Panzer engine required complete teardown and rebuild every 800 to 1,000 kilometers. The Maybach HL-120, powering the Panzer III, needed servicing at roughly 900 kilometers. The HL-230 in the Panther, even sooner. And here sits an aircraft engine, adapted for tank use, that has run more than twice that distance through mud, dust, and combat conditions, and still appears serviceable. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Brecht makes a notation in his technical assessment. American engineering philosophy, fundamentally different from ours. Emphasis on endurance over precision. Implications require further study. He does not yet know that this alternative philosophy has already decided the outcome of the war as surely as any battle or strategic bombing campaign. When we speak of World War II's decisive factors, we discuss firepower, tactics, industrial capacity. But wars are not won solely by the weapons that fire. They are won by the weapons that keep firing, by the machines that run when others have stopped, by the engines that carry soldiers forward while the enemy's vehicles sit silent by the roadside, abandoned for lack of parts or time to repair them. The M4 Sherman was never the best tank on any battlefield. The German Tiger could penetrate its armor from 2 kilometers away. The Panther was faster, better protected, and mounted a superior gun. The Soviet T-34 had revolutionary sloped armor and excellent mobility. Yet the Sherman became the symbol of Allied victory, not despite its limitations, but because of a single overwhelming advantage. It worked consistently, reliably, again and again. From 1942 to 1945, the United States produced 49,234 Sherman tanks. Germany, by comparison, built 1,347 Tigers and roughly 6,000 Panthers across the entire war. But the true disparity was not in production numbers alone. It was in operational readiness. A German Panther division might field 100 tanks on paper, but have only 40 operational at any given moment. An American armored division with 100 Shermans could typically count on 85 to 90 being combat ready. The difference was the engine. At the heart of the Sherman sat the Continental R975 EC2, a 9-cylinder radial aircraft engine producing 400 horsepower at 2,400 revolutions per minute. It weighed 238 kilograms and possessed a service life that seemed fantastical to German engineers trained in the cult of precision. And this is the story of how industrial philosophy shapes military outcomes, of how the choice between perfection and reliability, between craftsman and mass production, between elegant complexity and crude robustness can determine which armies advance and which armies halt. It is the story of an engine that was never supposed to go into a tank at all, and how that accident of necessity became one of the Allies' quiet, unglamorous advantages. 1940, Aberdeen Proving Ground, Maryland. American military engineers face an urgent problem. The new M3 medium tank, soon to be nicknamed the Lee, desperately needs a reliable power plant. In Europe, German panzers have demonstrated the effectiveness of mechanized warfare. Speed, maneuver, and mechanical endurance now decide battles. The United States is dangerously behind. Tank development has languished through the 1930s, starved of funding and attention. There is no time to design a purpose-built tank engine from scratch. Development cycles for new engines typically require 3 to 5 years. America does not have 3 years. It may not have 3 months. William Knudsen, former president of General Motors and now coordinator of war production, makes the critical decision. They will adapt an existing aircraft engine for tank use. The Continental R975 has been in production since 1936 for light training aircraft. The Boeing Stearman PT-17 trainer flies with this engine, as do several civilian aircraft. Training aviation demands maximum reliability. A student pilot cannot afford engine failure. Lives depend on engines that start reliably and run predictably. The R975's design is inherently suitable for harsh conditions. Its 9 cylinders are arranged radially around the crankshaft in a star pattern. It is air-cooled, eliminating radiators, water pumps, hoses, and the complex cooling systems that so often fail under combat stress. Each cylinder is a modular unit that can be replaced individually without requiring complete engine disassembly. For mechanics working in field conditions with limited tools and time, this modularity will prove invaluable. Continental Motors receives the contract in June of 1940. Engineers immediately begin adaptation work. The basic engine architecture remains unchanged, but modifications are necessary. For tank installation, air filtration systems are reinforced for dust protection. Exhaust routing is redesigned for the confined engine compartment. Bearings are strengthened to handle vibration levels far exceeding aircraft norms. All modifications are completed in less than 3 months, a remarkable achievement by any standard. By October of 1940, the first M3 tanks with Continental engines undergo trials. The sound is distinctive, a high-pitched aircraft tone rather than the deep rumble of purpose-built tank engines. Mechanics joke that their tanks do not drive, they fly at ground level. Initial tests confirm the essential characteristics. The engine handles sustained overload without complaint. It operates reliably from -30 degrees to +50 degrees Celsius. It does not stall after waterfording. Most importantly, it averages between 1,500 and 2,000 kilometers before requiring its first serious inspection. Against German tank engines of the period, considered reliable if they managed 800 to 1,000 kilometers, this performance represents a categorical leap in endurance. But the numbers alone do not explain the significance. To understand why German mechanics would later stare in disbelief at American engines, one must understand the engineering philosophy that created German power plants. The Maybach HL-120 TRM, which powered the Panzer III and early Panzer IV models, epitomized German engineering values. It was a 12-cylinder V configuration, liquid-cooled, producing 300 horsepower. Every component was machined to exacting tolerances. Pistons were individually matched to cylinders. Clearances were held within hundredths of a millimeter. Crankshafts were hand-balanced. The result was an engine that ran smoothly, quietly, and efficiently under ideal conditions. But ideal conditions rarely exist in war. The HL-120 proved exquisitely sensitive to environmental stress. In North Africa, desert dust killed engines at 500 to 600 kilometers. Fine sand particles penetrated air filters, infiltrated the gap between piston and cylinder wall, and scored the precision machine surfaces. Compression dropped, power vanished, engines seized. On the Eastern Front, winter cold thickened lubricating oil to the consistency of tar. Cold starts subjected precisely fitted components to shock loads they were never designed to withstand. Blocks cracked, bearings failed, gaskets ruptured. Repairing a Maybach in the field was a nightmare. Replacing the piston group required at least 2 days of work by an experienced mechanic. Truing a warped crankshaft consumed another full day. Valve adjustments demanded hours of patient work. Special tools were mandatory. The average field maintenance crew lacked both the tools and the expertise. With the introduction of heavier tanks, Germany's engine problems intensified. The Maybach HL-230P30, designed for the Panther and Tiger, was a masterpiece of automotive engineering and a catastrophe of field reliability. 700 horsepower from 23 litres of displacement represented cutting-edge specific output, but the engine chronically overheated. The cooling system could not manage sustained thermal loads. Carburetors suffered from vibration-induced failures. The transmission could not handle the torque without premature wear. The average HL 230 required major service every 600 to 800 kilometers under combat conditions, often less. A report from the 11th Panzer Division in March of 1944 noted of 20 Panthers delivered to the front, 7 broke down during the road march and 4 failed after the first engagement. Not one has covered more than 400 kilometers without requiring significant repair. German precision had become German fragility. Where the battlefield demanded a sledgehammer, German engineers had delivered a surgical instrument, beautifully crafted, but too delicate for the chaos of mechanized warfare. Detroit, 1941. Continental Motors operates in 3 shifts, 24 hours a day. The plant roars with activity as mass production of the R975 ramps up. Chief Engineer John Dorman stands beside the assembly line, explaining the philosophy to newly hired workers. "We are not making a watch," he tells them. "We are making a hammer. It must strike, not decorate." American engineers deliberately build reserve strength into every component. Cylinder walls are thicker than calculations strictly require. Piston clearances are wider, measured in tenths of millimeters rather than hundredths. To a German engineer trained in precision manufacturing, this would appear wasteful. Wider clearances mean lower compression ratios, reduced thermodynamic efficiency, and marginal power loss. But American thinking follows a different logic. Wider clearances mean sand and dust particles can pass through the engine without seizing moving parts. Thermal expansion under overheating conditions does not cause binding. Variations in oil viscosity do not stop the engine. The R975 can operate on 87-octane aviation gasoline, 80-octane automotive fuel, or even captured German benzene. Power output varies, but the engine continues running. The radial configuration provides additional advantages. Each of the 9 cylinders operates as an independent unit. If one cylinder fails due to combat damage, the tank continues moving on 8 cylinders. Power drops by approximately 11%, but the vehicle remains mobile. A crew can reach safety rather than becoming stranded under fire. Replacing a damaged cylinder in field conditions requires approximately 4 hours for 2 mechanics. No engine disassembly, no special tools, loosen bolts, remove cowling, extract the failed cylinder, install a replacement, reconnect the push rods, and the repair is complete. Air cooling eliminates the most common failure mode of liquid-cooled engines. No radiators to be punctured by shrapnel, no water pumps to fail from vibration, no hoses through which coolant leaks at critical moments. 4 powerful fans force air through the cylinder fins. The system is simple, reliable, and nearly impossible to break completely. The lubrication system demonstrates similar redundancy. 2 oil pumps instead of 1. If the primary pump fails, the secondary engages automatically. Dual oil filters. A large sump holding approximately 30 liters of oil acts as a thermal buffer, preventing rapid temperature spikes. Starting a German Maybach demanded ritual. Prime the fuel system. Set the choke correctly. Allow oil to circulate and in freezing conditions, warm critical components with blowtorches. The Continental R975 requires turning the key and pressing the starter button within 5 to 7 seconds. The engine is running, even at minus 25 degrees Celsius. American tank crews joke that their Shermans start faster than they can say, "Good morning." Statistics from General Patton's 3rd Army maintenance units in December of 1944 tell the story. Of 350 Sherman tanks passing through routine inspection, 320 showed no engine issues whatsoever. 25 required oil and filter changes, routine preventive maintenance. 5 needed a single cylinder replaced due to minor damage, not one complete engine failure. Compare this to German Panthers during the Ardennes offensive that same month. Approximately half were disabled on the road march due to engine and transmission failures, not from enemy action, from cold weather and mechanical stress. The American formula was simple. Better a tank delivering 90% effectiveness all the time than a tank capable of 100% that spends half its operational life awaiting repair. Field commanders learned this lesson quickly. They would rather have 80 Shermans running than 100 Panthers with 40 in the shop. November of 1942, Operation Torch. Allied forces land in North Africa, and Sherman tanks meet German armor in sustained combat for the first time. The desert is the cruelest test for mechanical systems. Sandstorms reduce visibility to zero and infiltrate every crevice. Temperature swings of 45 degrees between day and night stress metal components. Dust particles, finer than talcum powder, act as abrasive grinding compound inside engines. The British already know the cost. Their Crusader and Valentine tanks have suffered catastrophic failure rates. Air filters clog within hours, engines overheat, pistons seize. Entire armored formations are immobilized not by enemy fire but by environmental conditions. American planners brace for similar problems. They increase spare parts, stocks, reinforce maintenance units, and prepare for high attrition rates. The Sherman surprises them. Captain James Lear, maintenance company commander for the 1st Armored Division, records in his diary on November 15th, 1942, "Third day in the desert, expected half our tanks to experience engine trouble. Instead, 3 clogged air filters, 20 minutes to clean each one, engines running steady." His entry from December 3rd reads, "Covered 400 kilometers by road march. Not a single Sherman failed due to engine issues. In contrast, a British battalion abandoned 5 vehicles along the route." The secret lies in the R975's air filtration system. The design uses a 2-stage process. First, a cyclone separator uses centrifugal force to throw large particles out of the airstream. Second, an oil bath traps fine dust. Finally, a paper element catches remaining contaminants. Servicing requires removing a cover, pouring sludge from the oil bath, wiping surfaces clean, and reinstalling. 15 minutes of work. German Maybach filters are more compact but clog faster and require complete replacement rather than cleaning. January of 1943. The Battle of Kasserine Pass. American forces suffer their first major defeat against Rommel's Afrika Korps. The tactical verdict is harsh. American units were outmaneuvered, outfought, and poorly coordinated. Panzer IVs and several Tigers shattered inexperienced formations. But the technical assessment tells a different story. Of 48 Sherman tanks knocked out in the battle, 42 were destroyed by enemy fire. 6 sustained mechanical damage to transmission or running gear. Not one engine failure. By comparison, of 15 German tanks committed to the engagement, 3 seized from overheating on the approach march, and 2 would not start after an overnight halt in the cold. Rommel writes to his wife in February of 1943, "The Americans fight inexpertly, but their machines are impressive. Their tanks do not break down. There is scarcely anything more frustrating in war than facing an opponent whose equipment is inexhaustible." By May, when the Afrika Korps surrenders in Tunisia, the statistical picture is conclusive. Sherman tanks averaged 1,800 to 2,200 kilometers across African roads and desert terrain. The average Maybach engine in identical conditions lasted 600 to 800 kilometers before requiring complete rebuild. Captured Sherman tanks are transported to Germany for detailed technical study. Engineers at the Waffenamt disassemble engines, measure clearances, analyze materials, and examine manufacturing techniques. They cannot understand how an engine with such loose tolerances runs reliably. Where is the German precision? Where is the optimized efficiency? A technical report dated June of 1943 states, "The American Continental engine is more primitive than the Maybach in design. Lower specific output, lower thermal efficiency. Yet, service life is 2.5 times greater. Recommend revision of manufacturing standards to incorporate greater tolerance for wear." The recommendation is ignored. In Germany, precision engineering is a matter of national pride and industrial identity. Standards cannot be lowered to accommodate crude American methods. It will prove one of the war's fatal miscalculations. 1943. Two factories, two philosophies, two different visions of how machines should be built. The Maybach plant in Friedrichshafen, Germany, employs highly skilled craftsmen, many with pre-war experience building luxury automobile engines for Mercedes-Benz. Assembling one HL230 requires approximately 180 labor hours. Pistons are individually matched to cylinders using precision micrometers. A mechanic measures the bore diameter at multiple points, then selects the piston that provides optimal clearance, typically 12 to 15 hundredths of a millimeter. Crankshafts are balanced on specialized rigs, adding or removing tiny amounts of material until vibration is eliminated. Valves are hand-lapped to their seats, a painstaking process ensuring perfect sealing. Quality control is exhaustive. Every engine undergoes a full 12-hour break-in run under varying loads. Engineers listen for abnormal sounds, measure vibration levels, check thermal behavior, and verify oil pressure across the operating range. Monthly production capacity ranges from 150 to 200 engines, occasionally reaching 300 with maximum effort. Continental Motors in Detroit operates on assembly line principles perfected by the automotive industry. Workers include former farmers, housewives, and students. Training lasts 3 weeks. Then they join the line. Standardization is absolute. Pistons are fully interchangeable. Any piston fits any cylinder within specified tolerances of 0.2 of a millimeter. Crankshafts are cast to forms that inherently account for balance. No hand-tuning required. Assembly of an R975 takes approximately 22 labor hours. No lapping, no individual fitting, no artisan craftsmanship. Every bolt is torqued with a calibrated wrench to specified values printed on instruction sheets. Workers follow numbers, not feel. Quality control is simplified yet systematic. Every 10th engine undergoes complete bench testing. The remainder receives selective checks of critical parameters. Does it start? Does it maintain oil pressure? Is compression within acceptable limits? If yes, market approved and ship it. Monthly production throughput exceeds 1,500 engines. In 1944, the rate increases to 2,000 per month. The mathematics is stark. In 1 year, Continental produces as many engines as Maybach manufactures in 5 years, but the difference is not merely quantitative. An American engine can be repaired with parts from any depot in any theater. A piston, manufactured in Detroit in January, fits an engine assembled in Chicago in July. Perfect interchangeability across batches and production dates. A German Maybach from batch number 3421 requires parts calibrated specifically to that batch. Universal spare parts do not exist. Parts must be matched, fitted, and sometimes hand-modified for proper function. Sergeant Robert Miller, mechanic with the 4th Armored Division, later recalled, "We swapped cylinders on Shermans right in the field, open the shipping crate, grab the first cylinder, bolt it on. The engine runs. No measuring, no fitting, no fuss." German mechanics could not do that. Oberfeldwebel Kurt Schulz of the 116th Panzer Division remembers. To repair a Panther engine, you needed a special requisition listing tank serial number, engine number, and batch number. Then you waited for the depot to locate and send the correct part, sometimes a week, sometimes never. The tank sat idle while the front kept moving. Summer of 1944. Normandy. Allied forces break out from the beachhead. German forces retreat across France, abandoning equipment as they go. American recovery units discover dozens of serviceable Panthers and Panzer IVs left behind by their crews, not because of enemy damage, but because of minor failures that cannot be repaired without proper parts and tools. A turret traverse gear strips its teeth. The tank is abandoned. A cylinder block develops a crack. The crew scuttles the vehicle. One carburetor fails in a twin carburetor system. They leave the tank by the roadside and withdraw on foot. Allied Sherman tanks sustain battle damage, but are towed to field repair stations, fixed within 18 to 24 hours, and return to combat. Statistics from General Leclerc's 2nd French Armored Division in August of 1944 show that of 120 Sherman tanks, 87 sustained some form of damage during a month of continuous combat. 81 were repaired and returned to service. Average repair time was 18 hours. The Germans sarcastically dubbed the Sherman the Tommy Cooker for its tendency to burn when penetrated. Yet, this supposedly flawed tank kept returning from repair shops again and again. Its engine refused to give up. December of 1944, the Ardennes Forest. Germany launches its final major offensive in the west, Operation Wacht am Rhein, Watch on the Rhine. Temperatures plunge to -20 degrees Celsius. Snow blankets the landscape. Ice glazes roads. Frozen mud is hard as concrete. The worst possible conditions for machinery. The Germans prepare meticulously. Panther and Tiger units stockpile handheld blowtorches for warming engines. Detailed winter starting procedures are distributed. Lubricant allocations are increased so crews can replace thickened oil with lighter grades more frequently. But reality exceeds planning. Morning of December 16th, 1944, the first day of the offensive. The 6th SS Panzer Army must rupture Allied lines and drive for the Meuse River. In its ranks are hundreds of Panthers, dozens of King Tigers, the newest and most powerful tanks Germany can field. By noon, approximately 1/3 of the vehicles will not start. The Maybach HL 230 refuses to turn over. Oil has thickened to the point where electric starters cannot rotate the crankshaft. Mechanics warm engines with blowtorches, a process requiring 40 to 60 minutes per tank. The lightning assault bogs down before it begins. Columns clog narrow forest roads as disabled vehicles block those still operational. SS Obersturmbannführer Joachim Peiper notes in his after-action report of 72 tanks and self-propelled guns. On the morning of the 16th, 18 could not move due to engine failures. 9 more broke down within the first 3 hours of the march. We lost momentum before engaging the enemy. For American forces, the attack is also a surprise. Lines are pierced. Units retreat in confusion, but their machinery functions. Captain Charles MacDonald of the 2nd Infantry Division recalls, "A bitter morning. Orders arrive. Fall back immediately. The Germans have broken through. We climb into a Sherman that has sat all night in sub-zero cold. The driver turns the key. The engine catches on the first attempt. As always. We never imagined it could be otherwise." The air-cooled Continental R 975 proves more resilient in extreme cold than liquid-cooled Maybach systems. No antifreeze to freeze and crack blocks. No water hoses to rupture. No pumps to seize under frozen pressure. The lubricant is standard winter-grade SAE 10W. American forces maintain their equipment on schedule. Germans are forced to improvise with whatever materials can be scavenged. After 1 week of fighting, the pattern is unmistakable. Each German panzer division loses 30 to 40% of its strength, not to enemy fire, but to breakdowns and fuel shortages. The U.S. Third Army, by contrast, maintains high operational readiness. Vehicles that fell back during the initial assault are quickly restored to service. Maintenance companies work in the snow, replacing track links, repairing battle damage, and swapping individual R975 cylinders. Colonel Clarence Beck, head of Third Army's maintenance services. In the coldest week of the Ardennes, we repaired 140 Sherman tanks. In 95% of cases, the problems were running gear and armor. Not a single engine failed from cold weather. When the German offensive collapses in January of 1945, Allied forces find across the Ardennes hundreds of abandoned Panthers and Tigers. Many show no visible battle damage. Inspection records note, engines and transmissions failed from overload, cold, and lack of lubricant. Crews simply abandoned the machines and withdrew on foot. The winter of 1944 to 45 proves a fundamental truth. Wars are not won by the loudest explosions. They are won by the quiet reliability of engines that refuse to quit. March of 1945. The Allies drive deep into Germany. The pace is relentless. Dozens of kilometers per day. Wehrmacht defenses crumble. Speed creates new forms of mechanical stress. Tanks operate continuously, without the static defense periods that allow maintenance. Everything bears the brunt of sustained tempo. Track links wear out in weeks. Suspension components crack from constant impacts at high speed. Transmissions overheat from endless shifting during rapid maneuvers. But the engines hold. Lieutenant James Bates, Maintenance Platoon Commander with the 9th Armored Division, records. In the last 3 weeks, we have repaired 67 Sherman tanks, replaced approximately 140 track shoes, 22 sets of road wheels, 18 gearboxes. On engines, only 8 single-cylinder replacements due to shrapnel damage. Not a single complete engine failure from wear. Field repair becomes routine, sometimes conducted under artillery fire. Sergeant William O'Brien of the 7th Armored Division recalls, Sherman number 27 took a shell fragment through the engine compartment. 2 cylinders were punctured. We dragged it back. My buddy and I swapped the damaged sections in 3 hours, refilled oil, started it. That same evening, the tank returned to combat. The Germans cannot do this. The secret is the R975's modularity. 9 independent cylinders. If 1 or 2 sustain damage, the remaining 7 or 8 keep the tank mobile. Replacing a section does not require pulling the entire engine. By contrast, a Maybach HL 230 with a single damaged cylinder often demands removing the complete power plant. A week of work under factory conditions. American forces move spare parts with forward columns, GMC trucks with cargo beds packed full of cylinders, pistons, bearings, gaskets, standardized components in marked crates, interchangeable across production batches and manufacturing plants. Germans depend on centralized depots, many already destroyed by strategic bombing or cut off by rapid Allied advances. Needed parts never arrive. Tanks sit idle. Crews wait helplessly. April of 1945. The Ruhr pocket. Encircled are over 300,000 German soldiers and hundreds of armored vehicles. After capitulation, American technical intelligence teams inventory the captured equipment. The report makes stark reading. Of 170 German armored vehicles examined, 112 were abandoned due to mechanical failures. Of these, 89 suffered engine and transmission problems that could not be remedied in field conditions. 23 simply ran out of fuel. Only 58 were destroyed by direct enemy fire. The irony is painful. Most abandoned vehicles were 60 to 70% serviceable. One steering gear fails. The vehicle is left behind. A cylinder block cracks. The tank is scuttled. A single specialized part is unavailable, and the machine is blown up by its own crew to prevent capture. Sherman tanks fight even with catastrophic damage. A vehicle missing one track is emplaced as a static firing position. The engine powers the generator. The turret rotates. The gun fires. A tank with penetrated side armor remains mobile. The engine carries it to repair facilities. A Sherman with a locked transmission can creep forward in first gear. Slowly, but it moves. A Panther with comparable damage becomes an immobile metal monument. Technical Lieutenant Ernst Weber of the 2nd Panzer Division recalls years later, "We could not believe what we saw. A Sherman knocked through by an 88mm round. Next day, it was back in action. Our tanks, a minor fault, and that was the end. We lost the war not only on battlefields, we lost it in repair shops." May of 1945, the war in Europe ends. Final statistics tell the complete story. Over the European campaign, the United States lost approximately 8,000 Sherman tanks irretrievably. Of these, roughly 6,700 to enemy fire, about 1,300 to accidents, mines, and other non-combat causes. Engine failures as a direct cause of irretrievable loss. Number fewer than 200 cases, approximately 2.5% of total losses. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Germany lost approximately 4,000 medium and heavy tanks during the same period. Of these, roughly 1,800 to enemy fire, about 2,200 abandoned due to breakdowns, fuel shortages, and impossibility of repair. The share of engine failures and non-combat technical losses exceeds 40%. The numbers speak clearly. German tanks died from their own fragility as often as from Allied guns. The war ends. but the story lives on in the memories of those who held wrenches rather than rifles. Hans Müller, former mechanic of the 116th Panzer Division, interviewed in 1952 for the Bundesarchiv. I repaired Panthers for 2 years. I loved that tank. Powerful, fast, beautiful lines. But God, how finicky. The Maybach engine was a masterpiece of engineering. Yes, but every repair became an ordeal. Once, near Caen, in 1944, our Panther number 401 overheated. The block warped. We waited 3 days for replacement parts. When they arrived, we spent 4 more days swapping the engine. The tank sat immobile for a week. Next to us, an American Sherman took a fragment hit in the engine bay. Their mechanic replaced 2 cylinders in 1 evening. Next morning, the machine drove away. That moment, I understood. We were losing, not because we fought worse, because our machines were built for parades, not for war. Robert Miller, mechanic of the 4th Armored Division, interviewed in 1968. The Continental R975 was our best friend, simple as a hammer. I could tear it down with my eyes closed. Most importantly, it always ran. I remember the Ardennes, minus 20 degrees, everything freezing. Germans couldn't start their tanks. Our Shermans fired up on the first turn of the key. The driver turned the ignition and the engine roared. We never imagined it could be otherwise. Once our tank hit a mine. Track ripped clean off, belly pierced. Fragments flew into the engine compartment. I looked inside. 2 cylinders shot through, but the engine was still spinning on 7. We limped 5 kilometers to the repair point under our own power. All war long, I never saw a Sherman stuck because the engine died. Not once. Track snapped, transmissions broke, armor got hold, but the motor kept going. Kurt Schultz, mechanic of the 2nd Panzer Division, from his personal diary in 1946. We were raised in the cult of German quality, precision, perfection of every component, and that ruined us. Our tanks were masterpieces, and masterpieces are fragile. The Maybach HL 230 required care like a thoroughbred racehorse, special lubricants, strict maintenance regimen, regular inspections. The American Continental was a draft horse. Rough, noisy, inelegant, but unshakable. I disassembled a captured Sherman after the war. I looked at those wide piston clearances, the simple bearings, the coarse castings, and thought, how can this even function? By our standards, it should be rejected, but it worked, and it worked precisely where our engines surrendered. Jean-Pierre Leroy, mechanic with the French 2nd Armored Division, General Leclerc's division, interviewed in 1960. We received Shermans in 1943 in North Africa. Before that, we fought in British and older French machines. The Sherman was different. The R975 demanded no special care, no rituals, no rare tools or unique expertise. Any mechanic could service it. A 20-page manual and you were operational. We drove from Chad to Paris, then to Strasbourg. Our Shermans covered thousands of kilometers through deserts, mountains, forests. The engines held. When we liberated Paris in August of 1944, I thought this tank carried us home without failing. The Americans gave us not only weapons, they gave us reliability. To understand why German mechanics refuse to believe in the Sherman's capabilities, we must examine the fundamental engineering philosophies of 2 civilizations. Germany, in the 1930s, was a nation of precision mechanics, chemistry, and optics. The traditions of Carl Benz and Rudolf Diesel ran deep. Every product was treated as potential art. Leica cameras, Carl Zeiss optics, Mercedes-Benz automobiles. Engineers were raised in a culture of perfection. A component must be ideal. Clearances, minimal. Efficiency, maximal. Compromise was seen as defeat. Ferdinand Porsche, creator of the Tiger tank, famously stated, "If a machine is not technically perfect, it has no right to exist." That philosophy produced masterpieces. Masterpieces suitable for peace, not war. The Maybach HL 230 was designed as the pinnacle of engine construction. 700 horsepower from 23 litres of displacement, roughly 30 horsepower per litre. For 1942, that was extraordinary specific output, but the price of perfection was complexity. The engine contained approximately 1,847 individual parts that had to interact with tolerances measured in hundredths of millimeters. Any deviation and the entire system fell out of balance. German designers believed if everything was done correctly, reliability would follow naturally. They did not build in what Americans called a fool's margin. They did not assume tanks would operate at maximum load continuously across broken terrain, that filters would clog with dust, that oil changes would be delayed because supply convoys were destroyed. America, in the 1930s, was a nation of mass production. The traditions of Henry Ford and the Wright brothers shaped industrial thinking. The priority was not perfection of a single component, but functionality of the complete system under worst-case conditions. The American engineer thought this way: the product must work in the hands of an inexperienced user in the harshest environment, with minimal maintenance. The Ford Model T was built for a farmer who had never read a technical manual. A village blacksmith with basic tools had to be able to repair it. That logic flowed directly into the Continental R975, wider clearances because the tank would operate in dust storms, complete interchangeability because there would be no time to hand-fit components, modularity because the mechanic might be a hastily trained civilian. Continental engineer John Dorman wrote in an internal memorandum in 1941, "We are building an engine for war, not for a showroom. It must survive everything soldiers will do to it, soldiers who have never read the manual and never will." The two philosophies collided on European battlefields in 1944 and 45. A German tank crew received a Panther with an 88-page engine operation manual, warm-up procedure charts, oil viscosity tables for different temperatures, and step-by-step starting sequences. An American tank crew received a Sherman with a 12-page manual. The essence was simple: turn the key, drive. If something breaks, call a mechanic. The result was predictable. German crews destroyed their perfect machines through imperfect operation. No warm-up, block warps, high RPM across rough terrain, transmission wears prematurely, missed oil change, cylinder scoring. American crews treated Shermans like tractors. No special care, no rituals, and the engines endured. Training statistics confirm the contrast. The German Panzer Training Center at Bergen, 1943 curriculum, 8 weeks of instruction with 2 weeks devoted to technical training on Maybach engines, starting procedures, shutdown procedures, maintenance schedules. United States Army training at Fort Knox, same year, 6 weeks total, of which 3 days covered technical basics: how to refuel, how to start, when to call a mechanic. The Germans trained specialists, Americans trained users. For a mass war, the latter proved vastly more effective. General Heinz Guderian, inspector of panzer troops, stated in a report to Hitler in March of 1944, "Our equipment is technically superior to the enemy's, yet we are losing tanks faster than we produce them. The problem is not design, the problem is reliability and maintainability in field conditions." Hitler did not listen. He demanded more Tigers and Panthers, greater firepower, thicker armor, larger caliber guns. No one demanded simplicity. And wars are won by simple things that work consistently. After the war, Allied intelligence services gained access to German archives, armaments office documents, technical summaries from armored units, maintenance records. The figures were harsher than they appeared during combat. A United States Technical Intelligence report from November of 1945, based on captured documents, provides detailed comparisons. Maybach HL 230P30, engine of the Panther and Tiger II, Average distance to overhaul in controlled bench tests, 800 to 1,000 kilometers. Real field service life, 600 to 750 kilometers. In severe conditions, desert heat, Arctic cold, continuous cross-country operation, 400 to 500 kilometers. Share of failures before 500 kilometers, approximately 23%. Average engine replacement time in field conditions, 48 to 72 hours. Special tools, required, 17 items. Personnel needed, 4 to 6 mechanics with specialized training. Maybach, HL 120 TRM, engine of the Panzer III and early Panzer IV. Average service life, 900 to 1,200 kilometers in controlled conditions. Field reality, 700 to 900 kilometers. Failures before 500 kilometers, approximately 15%. Replacement time, 36 to 48 hours. Special tools, required, 12 items. Personnel needed, 3 to 4 trained mechanics. Continental R9, 75 EC2, engine of the Sherman. Overhaul interval in factory testing, 1,800 to 2,200 kilometers. Field service life, 1,500 to 1,900 kilometers. In severe conditions, 1,200 to 1,500 kilometers. Failures before 1,000 kilometers, approximately 4%. Average time for complete engine replacement, 10 to 14 hours. Time to replace a single damaged cylinder, 3 to 4 hours. Special tools required, none. A standard mechanics toolkit suffices. Personnel required for full engine swap, 2 to 3 with basic training. For single cylinder replacement, 1 to 2. But the most devastating numbers concern parts availability. A document from the Oberkommando des Heer, German Army High Command, dated January of 1945 records. As of January 15th, 1945, German armored vehicles awaiting repair or parts, Panthers, 847 units, of which 623 await engines or transmissions, Tiger 1 and 2, 152 units, of which 89 await engines, Panzer IV, 456 units, of which 298 await engine components. Average wait time for engine parts, 18 to 35 days. Tanks, destroyed by their own crews, in December of 1944, due to impossibility of repair, 412. For comparison, United States First Army Maintenance Report for January of 1945 shows average wait time for Sherman parts, 2 to 4 days. Tanks written off due to impossibility of engine repair in December, 7. Share of tanks returned to service after engine repair, 94%. The economics speak even louder. Production cost of a Maybach HL 230, approximately 18,000 Reichsmarks, roughly $7,200 at 1944 exchange rates. Continental R 975, approximately $1,850. Labor hours for the HL 230, approximately 180 man-hours. For the R 975, approximately 22 man-hours. In the time required to build one Maybach, Continental produced roughly 8 R 975s for the price of one Maybach, approximately 4 Continentals. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. But the most significant metric is neither cost nor production time. It is kilometers actually driven by a tank before irretrievable loss. A British post-war Tank Technology Commission study from 1946 examined average operational distance from factory delivery to final loss. Tiger 1, approximately 680 kilometers. Tiger 2, approximately 490 kilometers. Panther, roughly 750 kilometers. Panzer IV, approximately 920 kilometers. Sherman, approximately 1,640 kilometers. Moreover, German tanks were lost due to technical causes or abandoned in roughly 60 to 65% of cases. Shermans, in approximately 84% of cases, were lost to direct enemy fire. The pattern is clear. German tanks drove to their deaths. American tanks drove to victory. The war in Europe tells only half the story. The Pacific Theater presented even harsher challenges for machinery. Humidity, 90 to 95%. Temperatures consistently above 35 degrees Celsius. Jungles, swamps, volcanic dust, salt air that corroded metal within hours. The Pacific Islands were mechanical hell. July of 1944, Saipan. In the Mariana Islands, United States Marine Corps lands with Sherman support. Conditions brutalize men and machines alike. Water is everywhere, in the air, on the ground, in every seam and joint. Metal rusts overnight. Electrical wiring shorts, lubricants emulsify into useless mixtures. German Maybach engines were never tested in such conditions. Japanese tank engines, Mitsubishi Type 100 diesels, theoretically more moisture-tolerant, constantly died from water contamination in fuel systems. But the Continental R975 runs. Sergeant Anthony Romano, mechanic with the 4th Marine Division, later recalled, "On Saipan, everything rotted. Your weapon rusted if you didn't clean it daily. Clothes stayed wet for weeks, skin peeled from fungal infections. But the Sherman started every morning. I would open the engine compartment, condensation dripping from every surface, water pooled in crevices. Turn the key. The engine thundered to life as if nothing was wrong." The secret was simplicity. Minimal electrical components, magneto-ignition sealed under rubber boots, air cooling, no liquid coolant to contaminate. The carburetor was primitive but nearly indestructible. September of 1944, Peleliu, one of the bloodiest Pacific battles. Temperatures exceeded 45 degrees. Coral dust rose in clouds, finer than desert sand, infiltrating everything. The Marines used M4A2 Shermans with General Motors diesel engines alongside M4A1s with Continental R975s. A 1st Marine Division technical report noted diesel Shermans proved sensitive to coral dust. Fuel systems clogged, injectors failed. 12 cases of complete engine failure from blocked filters. Shermans, with the Continental, 3 filter-related issues cleared by cleaning in 15 to 20 minutes. No complete failures. April of 1945. Okinawa. The final great Pacific battle. Torrential rains transformed the island into a quagmire. Tanks sank to their turrets. Lieutenant Colonel Robert Neiman, battalion commander. "We lost more machines to mud than to Japanese fire. We had to pull, tow, winch everything at maximum strain. Engines roared at redline for hours. The Continental held. 3 tanks operated 18 hours straight, hauling others from the mud. Not one broke down." Pacific Theater totals for 1945. Approximately 4,800 Sherman tanks fought against Japan. Lost to enemy fire, roughly 1,240. Lost to accidents and non-combat causes, approximately 380. Of these, due to engine failure. 47, about 12% of non-combat losses, and roughly 1% of total losses. For comparison, Japanese Type 97 Chi-Ha tanks, total losses approximately 2,100. To enemy fire, roughly 680. Due to technical failures, approximately 890, around 42% of total. The tropics proved it. The Continental R975 endures not only European winters and desert heat, it is genuinely universal. Japanese mechanics who examined captured Shermans experienced the same shock as Germans. A report by Imperial Army Technical Intelligence from August of 1944 states, "The American engine is primitive in design, yet extraordinarily resilient. Our Mitsubishi engines are technically more sophisticated, but far more sensitive to operating conditions. It is recommended to study American design approaches." As in Germany, the recommendation was ignored. An engineering culture fixated on theoretical perfection could not embrace practical simplicity and lost because of it. May of 1945, Europe lies in ruins. But machines remain. Thousands of tanks, guns, vehicles. The Allies transfer portions of their Sherman inventory to rebuilding nations: France, Belgium, Netherlands, Italy, Poland, and the Continental R975 keeps serving. Israel, 1948, the War of Independence. The young state acquires whatever it can find. Among its first armored vehicles are several Shermans purchased in Europe as surplus. The machines are 5 to 6 years old, have crossed France and Germany, then sat outdoors for years, exposed to weather. Israeli mechanics brace for complete engine rebuilds. Instead, they change oil, clean filters, connect batteries, and start the engines. The tanks are ready for battle. Menachem Raga, Haganah mechanic, recalls, "We received 3 Shermans from France. They had fought in 44, then rusted in the open for 2 years. I thought they were scrap metal. We filled them with fresh oil, connected batteries. The engines started. They just started. I could not believe it." The Sherman fights in Israel into the 1970s. The Continental R975 is eventually replaced with more modern power plants, but the basic reliability philosophy endures. France operates Shermans into the 1960s, first in Indochina, then in Algeria. The same engine, pulling through tropical jungles and North African mountains. Argentina, Chile, Paraguay purchased Shermans in the 1950s. Some serve into the 1980s. Everywhere, the pattern repeats. The engine is inefficient by 1960s standards, technically outdated, obsolete by modern metrics, yet reliable. 1952, West Germany forms the Bundeswehr. Americans transfer equipment, including Shermans. German mechanics, many with Wehrmacht experience, face the Continental R975 again. Oberfeldwebel Ernst Kleiner, former mechanic of the 21st Panzer Division, later a Bundeswehr instructor, writes in a 1954 training manual, "The Continental engine is structurally simple and does not meet our traditional precision standards. It is precisely this simplicity that ensures exceptional reliability. A German mechanic must abandon familiar assumptions about tight tolerances. This engine operates by different principles, and it operates well." Recognition arrived too late to change the war's outcome. Continental Motors produces the R975 into the 1960s. Total production exceeds 54,000 units. Maybach HL 230, approximately 9,000 over its entire production run. After the war, Maybach attempts to rebuild its engine business, but the reputation for technical sophistication, combined with poor field reliability, lingers. The Continental R975 becomes a legend, not for record-breaking power or extraordinary efficiency, but because it always worked. The story of the R975 is not merely about an engine, it is about an engineering philosophy that helped win a war, a lesson often undervalued. The 1960s, the United States fights in Vietnam. New hardware arrives, new tanks, the M48 Patton, the M551 Sheridan, complex power plants, electronic fire control, hydraulic transmissions, and catastrophic unreliability. The M551 Sheridan, aluminum armor, missile firing gun, diesel-electric transmission, a technological marvel on paper, a nightmare in service. A 1969 field report from Vietnam states, Sheridans fail more often than they fire, the transmission cannot withstand jungle humidity, electronics short from condensation, mean time between failures approximately 50 operating hours. A veteran mechanic who serviced Shermans in 45 and Sheridans in 68 summarizes, "We forgot the lessons. The Sherman was simple, it rarely broke. The Sheridan is complex, it breaks constantly. We followed the German path and achieved German results." The 1980s, the M1 Abrams with its AGT 1500 turbine engine, 1,500 horsepower, jet engine technology and a tank, reliability improves over the Sheridan, but remains inferior to simple diesels. Fuel consumption, approximately 400 liters per 100 kilometers. The R975 burned roughly 200 liters over the same distance, with a fraction of the power. The turbine's real-world efficiency is significantly lower. Servicing the AGT 1500 requires specialized equipment. Swapping the turbine demands 8 to 10 hours for a team of 4 skilled mechanics. Replacing a single R975 cylinder, approximately 3 hours for one experienced technician. Is that progress or repetition of old mistakes? Modern armies relearn at high cost what should never have been forgotten. Russia's operations in Ukraine from 2022 onward. High-technology T-90M and T-80 BVM tanks often sit immobile due to minor electronic failures. Complex fire control systems fail under vibration. Field repair shops without factory-grade tools are helpless. Older T-64s and early T-70s, cruder and simpler, sometimes outlast their sophisticated descendants. History repeats. Excessive complexity loses to fundamental simplicity once again. Perfection loses to reliability. You can still see Continental R975 engines today in museums, at historical reenactments, in private collections, and if you fill one with fresh fuel and oil after 80 years of existence, it will rumble to life. Because some things do not age, they simply work. History is not written only by generals and politicians, it is created by engineers drawing lines on blueprints, workers tightening bolts on assembly lines, mechanics lying beneath tanks in frost and heat. The Continental R975 was never the war's most powerful engine, not the most efficient, not the most elegant. On paper, the German Maybach surpassed it in nearly every metric except one. Reliability is not measured in horsepower specifications. It is measured in kilometers driven to victory, in hours a mechanic does not spend on repairs, in the lives of soldiers who do not die inside a disabled hulk under enemy fire. German mechanics did not believe an American engine could run 1,500 kilometers without major intervention. They viewed the world through the lens of precision, efficiency, perfect engineering. But war is not an engineering problem with an optimal solution. It is chaos, dust and mud, cold and heat, overloads, impacts, vibrations. A rookie mechanic who never read the manual. A soldier pouring whatever oil he can find because correct lubricants are unavailable. In that chaos, the winner is not perfection. It is what refuses to stop. Americans understood this earlier than others. They did not craft a masterpiece. They built a tool. Rough, loud, not particularly economical, but tenacious beyond measure. The Continental R975 became the heart of the Sherman tank, and the Sherman became the symbol not of superior armor or firepower, but of industrial endurance, of the machine that was always present where needed. It drove, it fought, it returned. The statistics remain stark. Of 49,234 Shermans produced, approximately 8,000 were irretrievably lost in combat. Fewer than 200 losses were directly attributable to engine failure. Germany built roughly 6,000 Panthers. More than half were lost to technical problems that could not be resolved in field conditions. Wars are not won by tanks as abstract concepts. Wars are won by tanks that move forward when others have stopped. Nearly 80 years have passed since the war's end. The lessons of the R975 remain relevant. We are still dazzled by complexity. Electronics, artificial intelligence, autonomous systems. We design machines that demand narrow specialists and controlled conditions. Yet in war, the specialist is not present when needed. Spare parts never arrive on schedule. Reality never matches the technical manual. The winner is not the smartest machine. It is the machine that functions when the specialist is dead, when the parts depot is destroyed, when conditions exceed every specification. In the spring of 1945, German mechanics stood over a disassembled Continental R975 and could not comprehend. How can something so simple work so reliably? Where is the precision? Where is the sophistication? They looked in the wrong place. Sophistication was not in individual components. It was in the philosophy. The best component is the one that does not break. The best engine is the one that does not require genius to maintain. The Continental R975 did not defeat the Maybach HL230 on technology. It won on concept. That lesson deserves remembering in a world where complexity often becomes an end rather than a means. Sometimes the optimal solution is not the most elegant. Often the victor is not the fastest starter, but the one who reaches the finish line. The R975 reached it. It roared, it smoked, it was never quiet, but it ran. From African deserts to Ardennes frost, from Pacific jungles to German streets, it carried its crews forward. And when the last Sherman halted beside the Reichstag in May of 1945, its engine was still running. It was not the prettiest triumph of engineering, but it was victory. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.